This is problem 43 in chapter 18, and I've already redrawn their picture here. And we've got our positive, our negative plates, and we have a uniform E field in here. I'm not really going to draw that. Just look at their picture. I don't want to get my picture too messy. But you'll see the lines are evenly spaced, so the E field is the same everywhere. And they give us an angle of 30 degrees, and they want us to find the magnitude of the charge on each one of these plates. If you're trying to find the charge on a plate, we don't have too many equations for capacitors yet. In fact, for charge on a plate, there's only really one where that comes in, and that is the strength of the E field equals sigma over, I believe it's epsilon naught. Let me double check. Yeah, epsilon naught. And my sigma is not the prettiest thing in the world. Let me zoom and show you here. There's what, oh, actually, mine's reversed. So there's their printed sigma. Okay, but you get the idea. And then over epsilon naught, which is something you just look up. So this is something we already know. I'm going to check by that. And what is sigma? Well, that's charge on a plate divided by area. And then we still have this all over something we look up. Well, in the problem, the area was also given, and that's a tip-off that you're going to use this equation as well. So I'm going to put a check by area. So what we're really trying to do to find the E field, or excuse me, to find the charge on each plate is to find the E field. Because we're looking for, we have area, we have epsilon naught. In fact, I think we also have, yeah, we have area and epsilon naught. So if we can get E, we can get the charge on the plate. This is not the charge that is hanging from this string. Okay, this is the charge on one of these plates. So we want the charge here. So we want the charge on that. We are given the charge, this point charge, but that is not the same thing as the charge on the plates. So if we can get the E field, again, I'm kind of working backwards like the last problem. If you watched it, I'm kind of working backwards from, okay, what do I need to be able to solve for this charge? And there's only one equation. So if I can get E field, I'm home free. So what else does E field equal? Well, we know E fields and forces are related by this. So if I'm going to start dealing with forces, I'm going to draw a free body diagram. And you hopefully, if you get stuck on a problem and you're dealing with E fields or forces, you draw either a free body diagram or what the E field looks like at a point. That's a skill you need to be able to do. So let's run through this. So we're considering the E field lines to be going from positive to negative, like they always do. So for a positive charge, that'll push this to the right. So we'll have a force of the E field to the right, and that should be directly to the right. We have tension, goes in the direction of the rope. And remember, ropes can't push, they can only pull. Okay, so tension's up and to the left. And then if they gave us a mass, which they did, they gave us a mass, they didn't say to neglect it or anything, I'm also going to include weight. These are not necessarily drawn to scale, but there's the free body diagram. Tension up and to the left, weight down, and force of the E field to the right. And again, that's because our E field lines are going to the right from positive to negative, and we have a positive charge. So the force is in the direction of the E field. This is a positive charge. And I'm trying to get this E field. So if I can get this force, and remember I'm getting the E field so I can go back and get the charge and all that. If I can get this force, I'm home free because they told us the charge was 0.15 microcoulombs on this thing that's suspended here. They told us some other information there as well that, what did they say here? Somewhere they should say equilibrium, or yeah, the ball is in equilibrium, or they might say something like the ball isn't moving, whatever. That's just letting you know that your acceleration in both directions is 0. So when I sum forces now, and I can do it in both directions, probably will need to, I get to say equals 0. So let's keep going. I'm going to say in the x direction, we have force of tension in the x to the left. So I'm going to go ahead and make that negative, plus the force of the E field equals 0. And so we have force of E field equals force of tension in the x. So it looks like I'm stuck there. I can do one more substitution. I could put in an ft cosine or sine theta. We'll see if we need that here in a minute. So summation of forces in the y equals 0. So I have a y component of the tension going up minus the weight equals 0. And now I can get tension in the y equals the weight. And it looks like the rest is going to be a bunch of algebra except relating the x to the y. You could do this with tangent, which I might do, or most of you prefer the substituting in for ftx and fty. Doesn't really matter as long as you can get there algebraically, but let's plug in some numbers here. So force of weight, we've got 6.5 times 10 to the minus 3 kilograms times our 9.8. So we can see that we can get that number. And then what I would probably do, I'm going to draw my triangle up here. I'm going to go ahead and use, I think, the tan theta just to show you something different. What I'm referencing the other way is you could make this like ft cosine theta and ft sine theta, solve this for ft, plug in here, and then go back. I'm going to relate them with theta. So here's the 30 degrees on my picture. That's the angle right here is the 30. And here's my ftx. Here's my fty. So the tangent of 30 degrees equals the opposite, ftx, over the adjacent, fty. So now I have a way to relate the x to the y direction, and I got the y component, which means I can get the x component, which means I can get fe. So let's go ahead and do that. So fe, I guess I better solve up here to make this clear. We're looking for tension in the x. So tension in the x will be tan 30 times fty. So this will equal fty tan 30. And again, that just came from right here. Okay, so we've got force of E field, substituting in ftx equals, just multiply both sides by fty tan 30, and here's fty. So I just need to take this number and multiply by tangent 30, and that'll get my E field. So let's go ahead and get these numbers into here. 6.5 times 10 to the negative third. Oh, yeah, times 9.8. So okay. 0. Oops, that's a 0. 0.0, that's a 0. 0.0637 newtons. That times tan of 30. Just make sure you're in degree mode. I check as well. Yep, we are. Times tan of 30. And we get something small, 0.036, we'll call it 8. 0.0368 newtons for my force of the E field. Now I need to go back and get the strength of my E field. So I'm going to put this in up here. So 0.0368 over Q naught, which we were given. The charge in the field is 0.15 microcoulombs. I'm going to do this somewhere else so it's not so messy. Let's do this down here. E field equals F over Q naught. So I'm just rewriting this equation I had up here. So our force to our E field is 0.0368 over our charge, 1.6. Oh, no. What was it? 0.15. So 0.15 microcoulombs, so 10 to the minus 6 coulombs. And that'll get us our strength of the E field. So I'm just going to take this number. Yeah, I should really round it off. Divided by 0.15 times 10 to the negative 6. And we get some huge number, 245,181. And again, you could use scientific notation here if you want, newtons per coulomb. A reasonable number of digits for the actual AP test. I would probably, I might go 245 and then 3 zeros. That would be close enough. Newtons per coulomb. Now working back to the charge per unit area, I'm going to do this on the back. I'm just going to rewrite what I have here equals E field, and then take that number. So E field equals charge over area over epsilon naught. And we have our E field is, let's go ahead and round that off, 245 and then some zeros. 245 newtons per coulomb. Make sure I got the right number. 245, yep. Equals charge over area. Charge is what we're solving for. Area of a plate was 0.015 given in the problem. 0.015 meters squared. And epsilon naught, I have no idea. I will look at the key again just to grab the constant. Epsilon naught, they got it out front. So it's here, 8.85, and it's on your table of information. Epsilon naught times 10 to the negative 12th. And then a bunch of units. Coulomb squared over newtons times meters squared. Units should work out to a unit of charge. And let's see what we get. So 245. Lots of places where things could have gone wrong here, just in terms of punching in numbers. 0.015. Let's see. 4.15 times 10 to the 14th. That seems like a lot, but I guess it's in coulombs. Let's see what they got. Let's see, it's 43. Uh-oh. Yep, that seems like too much. No, this isn't 43. Yeah, this is 43. They got something times 10 to the negative 8. Yeah, that's too much. So probably messed up right here. Let me double check. Let's see here, 8.85 times 10 to the negative 12. Did I plug in the wrong mass, possibly? No, I didn't plug in the wrong mass. We got that, 1030. That all looks good. So force divided by a charge, so this should be a big number. So it's got to be right here on the last step. I should be multiplying both sides by 0.015, yes. And then, oh, there it is, multiplying both sides by, yep, I messed up my algebra right here. Apologize. This should just be in the denominator the way I've written it, right, improper fraction, and I went and divided by that. So I'm just going to recalculate. This is correct. Everything that's written is correct. Stupid mistake. All right, and then times 0.015. Either that or I forgot a caret. There we go. So everything's fine. I just plugged in numbers wrong. 3.25 times 10 to the minus 8th coulombs. And that's what they got. Same thing. Again, lots of different ways to attack this. Even if you didn't see this at the beginning, the stuff I did at the beginning here, trying to kind of work backwards from what I was looking for, the other approaches, do what you know how to do. Draw a picture, draw a free body diagram, start summing forces, write down relevant equations, which will eventually lead you to this, which hopefully then will lead you to the connection to sigma. And then, of course, you have to know what sigma is. It's charge per unit area. If you have questions, feel free to come in after school. I'll show this weight one more time here, in case you're going right to the end and see the solution. And then that's it.